Hello and welcome back to Calculus 1 section 4.2 on the mean value theorem. This is a very interesting calculation, and let's see what we can do with it. Let's first have a little story. So here's a highway. Here's your car. Tires sticking out a little bit. All right, good. Do you want a spoiler? Sure, why not, huh? There. All right, so the car is moving forward to the left, this way. And here we have shrubbery. Now, what's usually hiding behind shrubbery in the highway? Deer. Deer. Oh dear. All right. So this deer is going to have a little bit red and blue on top, right there, right? Also some tires. And this deer is measuring the speed. Now, let's say it's 60 miles per hour. Speed limit. Now, obviously you invested in the radar detection, so you detected the detector and you slow down from your comfortable 170 down to 60, right? And you pass through the trap, and obviously because you're going 60, you are not pulled over, right? Drive down the road, another shrubbery, and another deer with the red and blue. There you go. Tires. Measuring as well. You are passing through the second trap. Your radar detector went off and you went through 60. So you passed through the first one at 60 miles per hour. You pass through the second trap at 60 miles per hour. No one pulled you over. There we go. But then you get a ticket in the mail. Now, usually when I have a lot of students in a classroom, someone self-identifies, or they know someone who just got a ticket in the mail for speeding without being pulled over. So, what's happening there and how? You know that your speedometer is showing the instantaneous speed, instantaneous rate of change, which is the derivative, right? And you know that when you get to change up or down by pressing gas or brakes. Those are both accelerators. Well, one is acceleration, the other one is deceleration, but they're both positive or negative acceleration. And they change speed. So if you go to the first one at 60 and the second one at 60, right, and not pulled over, right, then what else is a factor here, right? Now, the trick is that these two cars are 5 miles apart. You passed through the first gate, to the first, to the first trap at, let's say, 1:24 p.m. and then you pass through the second one at 1:28 p.m., making the difference of 4 minutes. So the first car was not just measuring the speed was also measuring, also gave a timestamp when you passed by. Yes. So now you know that the speed or the velocity is distance divided by time, because it's miles per hour, and you have 5 miles and you have 4 minutes. Now these 4 minutes need to go into hours, so you want to cancel minutes and get the hours. So 1 hour has 60 minutes, so minute and minute cancel. So this is 5 times 60 divided by 4, which works out to be 75. Very good. Miles per hour. So I hope you see what happened there, right? They calculated that your average speed between the two locations was 75. And now, in this section, we learn a theorem which connects that average calculation to the actual speed. And the formula says that if the function is continuous and differentiable, then they are the same at least once. So, is your trip continuous? Sure, you did not teleport, right? And is it differentiable? Yeah, because you have velocity, right, which is the derivative of position, and you have acceleration that is the derivative of velocity. So everything is differentiable, nice and smooth and continuous. So this theorem would apply. Now this means that at least once you were going 75. Now for a fact, we know that you were going more than that as well, because if you are averaging 75 and you pass the two gates at 60, right? You were going even more, but we can't mathematically show how much more than 75, so 75 is what you get quoted on. In the other class that I taught on Wednesday, a student said, "Oh yeah, my mother," and I said, "There we go." Right? So usually I have, if the classroom has 30, 25, 30 people sitting in it, usually someone says, "Yep, me." How do you implement this? Easy pass. You go to the first easy pass gate, you go to the second easy pass gate, right? They are certain amount apart. So, and somewhere on the road they've been testing this for a long time. I'm not sure if they're abandoning technology because autonomous car is coming up, but it was almost ready to be rolled out, put on all roads. And the only way to trick it is to drive as fast as you can, go through the gate, right, at exact speed that is maximum, and then before you are there for the next one, you park for 3 minutes and wait until the time ticks what it needs to be, and then you, I mean, there's no way you can trick this, right? Student said, well, had 2 easy pass accounts, and then just swap them, right? It's like, all right, fine. But this is it, right? So what is the theorem that we are learning? The theorem says, let f of x be continuous and differentiable on interval a, b, then there exists at least one c in AB such that the derivative at C is equal to f of b minus f of a divided by b minus a. What this is the formula, and what this formula says is that your slope of the tangent is equal to slope of the secant line. We can see this on the graph. Here's your A, here's your B, and here's your C inside A and B. And we see that the slope of the tangent and the slope of the secant line, so this is your tangent line, this is your secant line, and we know that parallel lines have the same slope, so that's what this is. This means that we can actually compute the value C. And we can compute value C if we have the function and the interval that we are interested in, because we have a function, right? We have a formula to calculate. So say you have that your f of x is equal to x cubed minus 2x squared minus 8x or negative 2 to 4. All right? So what I need is the derivative, f prime of x, which is simply 3x squared minus 4x minus 8. And now f prime of c is equal to f of b minus f of a over b minus a. You have your a and b over here. So just plug everything in. If f of x is equal to 3x squared minus 4x minus a, then f prime of c must be 3c squared minus 4c minus 8, right? Because the difference between these two is x is c. So plug in that there. Now, we have f of b, so that's going to be negative 2 cubed minus 2 times negative 2 squared minus 8 times negative 2 minus, open parenthesis, 3 times 4 cubed minus 4 times 4 squared. Using the wrong one. It's 4 cubed minus 2 times 4 squared minus 8 times 4. There we go. Divided by 4 minus negative 2. And as you can see, the only variable you have is c. You can calculate. 3c squared minus 4c minus 8 is equal to, and now we have to compute all of this. Well, the bottom is 6. That's easy. All right, what do we have up there? You have negative 8. And then you have minus 8. And plus 16. And minus 4 cubed, 64. And then this is 16 minus plus 32. And then minus plus 32. And they all cancel to 0. So 3c squared minus 4c minus 8 equal to 0. Great. We need to factor this one. Last time I factored, let me use the quadratic equation this time because we can. Negative b plus minus square root of b squared minus 2ac minus 4ac divided by 2a. So negative b, that's 4, plus minus square root of b squared is 16 minus 4ac. So 4, 3, and 8, and it's negative, so this is positive. 8 times 3 is 24, double, and then double. So 96 over there, divided by 2 times a is 6. And now I have 4 plus minus square root of, that's a 12, 112, right? Divided by 6. I don't like it. What's my derivative? 3, 4, 8. Did I copy this right? 3, 2, 8. Yeah, well, tough luck. It doesn't. C is not pleasant value, but such is life, right? Square root of 112, 10.6, so 4 plus minus 10.6 over 6. So you have two values, and since we are from negative 2 to 4, they both might be in. Let's see if we keep both. So 4 minus 10.6 divided by 6 is negative 1.1, and the other one is 14.6 divided by 6, 2.43. And my interval for this problem is negative 2 to 4, so we keep both because it's in the interval. Great. So we can calculate C. Let's find another C that it's maybe something with trig. Oh, it didn't work out because this was a Rolle's theorem. Okay, fine. Let's see something with woo. F of x equals ln 2x on interval 1 to e. Okay, so f prime of x, we know it's 2x, and then 2, which is 1 over x. So now f prime of c, that's 1 over c, is equal to function computed at b, so that's ln 2e minus ln of 2 times 1 divided by e minus 1. 1 over c is equal to, you can split this in a log, ln 2 plus ln e minus ln 2. Oh, this is cool, because these ln 2's cancel, and ln e is 1. So 1 over c is just 1 over e minus 1, which means that when you flip one fraction, you flip the other. C is simply e minus 1. So C is e minus 1. Well, that was much easier than it looked when we wrote the function down. Entire problem. You find the derivative, you replace each x with c, and that's the derivative side, and then you have on the other side f of b minus f of a divided by b minus a. Let's work on 32. So try this one on your own. Take the derivative, replace it with c's. All right, let's see. So we need the derivative, which would be, you can use quotient rule. So we have x plus 2 squared, x plus 2 times 1 minus, and then we have x times 1. So this is x and x will cancel, 2 over x plus 2 squared. So now replace that with a c. C plus 2 squared is equal to, plug in 2, so 2 over 2 plus 2 minus negative 1 over negative 1 plus 2 divided by 2 minus negative 1, which will be 3. I have 2 over 4. Minus and minus gives me plus 1. So 2 over c plus 2 squared is going to be 1/2, so that's 3/2 divided by 3, so that's 1/2. 2 divided by c plus 2 squared is equal to 1/2. Cross multiply, c plus 2 squared is equal to 4. Square this out, we have c squared plus 4c plus 4 equals to 4. C squared plus 4c equal to 0. And factor out c plus 4 equals 0, c equals 0, c equals to negative 4. Now we are on the interval negative 1 to 2, so this one is dropped because negative 1 to 2, and we keep our c equals 0. As far as application goes, we've seen the one with the speed trap. There are other problems that you can consider. The running pace, problem 45, the word problem with the runner who is going to complete 6.2 mile run in 32 minutes. It says he must have been running at 11 miles per hour at least twice. All right, let's try. So we have the complete 6.2 mile run. So the distance d, 6.2 miles, and time is 32 minutes. So velocity, the speed, is going to be 6.2 miles divided by 32 minutes. Again, we have to convert minutes to hours. And what I have is 6.2 times 60 divided by 32. Works out to be 11 point something, which is where the number comes from. 6.2 times 60 divided by 32, 11.625. So this is where 11 is. This is velocity in miles per hour, and this is time. You start with the velocity 0, you end your race with the velocity 0. When the race is done, you stop. And we see that the runner hit at least once more than 11 miles per hour, right? 11.625 miles per hour. That means that between 0 to reach that one had to cross 11, and then on the way back, right, from that higher value than 11 had to go back through 11 down to 0. So those are the two locations when the runner hit 11. Now we don't know what the runner's top speed was. Could be 12, could be 15, could be whatever, right? But the fact is that we know that the runner was doing 11.625 on average, which means that at least once his speed was 11.625, and because you start from 0, to get to 11.625, you have to go through 11, and then to stop, you have to go from 11.625 down to 0 through 11 again. So that's how we know that at least twice hit the 11 miles per hour. And that's it. Homework is open. Also 4.3 is open, but 4.3 is lengthy, so we don't have time to finish it now. Next class, next Saturday, we are going to cover 4.3, 4.4, 4.5, at least those. So 2 Saturdays will be done with chapter 4, and we'll start chapter 5. We can start thinking about exam 3. We only have 5 classes left. We are not in a rush or panic mode, but we don't have a lot. So I'll bring the exams next class, and I'll see you around. Bye.